Okay, electrical measuring devices. We're talking about voltmeters, ammeters, and general purpose multimeters. With these devices, they were originally analog, meaning that they were essentially constructed using electrical and mechanical devices and based on a galvanometer. A galvanometer was just simply a device where you'd send current through it, and depending on the degree of current, it would create a small electromagnet, would create a small magnetic field, and this magnetic field would interact with permanent magnets. The greater the current that you had passing through this, the stronger the magnetic field, the more torque that you would receive, and this would put torque on torsional springs, which would act against the torque. Therefore, a needle would move with these, the rotation of these torsional springs and indicate just how much current you have passing through this. If it were calibrated, then it could be basically an ammeter. It would measure current. Now, because many of these galvanometers were very, very sensitive to small currents, we would actually use a resistor in parallel with this to divert some of the current so we didn't overload the small windings in the galvanometer. And each of these resistors would have different values depending on how large of a current you wanted to measure. If you want to measure a very small current, you would hook it in parallel with a very high resistance, so most of the current would go through the galvanometer. As you progressively would go to higher current measurements, we would use smaller and smaller resistors, so the current would mostly go through the resistor rather than the galvanometer. You could dial these using a switch, or you could actually plug it into different things, but these analog ammeters were really quite simple, and again just had this simple galvanometer and some well-calibrated resistors. Similarly, you could create an analog voltmeter. In this case, instead of having the resistors parallel to the galvanometer, the resistor would be in series with the galvanometer. Therefore, depending on what voltage you wanted to measure, you could select either a small resistor. This would mean that the potential difference would be mainly across a galvanometer, drawing more current, or a higher resistor to put more voltage drop across the calibrated resistor, and again, less voltage across the galvanometer and less current through it. So again, using both parallel and series resistors, you could either take one of these galvanometers and convert it into an ammeter or voltmeter and then calibrate it. It's not to say that there weren't other devices that would use other mechanical means to do this. This was just a very convenient and very accurate way to do it. Digital voltmeters, of course, are very, very important and essentially use what's called an analog to digital converter, where we would convert some type of exterior voltage to a digital signal, which then could be read either on a digital scale or could be read by a computer, some type of microprocessor. Now, digital voltmeters basically use a very specialized analog to digital converter known as an integrating ADC. And without going into all the details, they would use a comparator circuit and essentially watch how long it would take the voltage to build up, and then compare it to connecting to a known voltage, how long it would take to ramp down. It would time this, and by comparing the two, could then convert this into a voltage. Likewise, a digital voltmeter could then become the basis for a digital ammeter. Remember, V equals IR, therefore I is equal to V over R. We could look at what the voltage would be across a precision resistor and then use that to determine what a current would be. In fact, many of these digital voltmeters are integrated into what's called a multimeter, where it could not only measure DC voltage and DC current, it's also set to measure other things such as AC voltage and AC current, where the voltage is actually changing polarity over time. It's actually oscillating. It can also act as an ohm meter, where it would send a fixed amount of current through a resistor and then use the potential difference to determine the resistance. Also measure the current. Capacitance meter can even be an inductance meter. But again, they're basically all using these digital voltmeters to convert an analog voltage into a digital signal. Now, switching back to how to use a voltmeter and how to use an ammeter, we did talk a little bit about this earlier. But as you might remember, we always place a voltmeter across whatever circuit element we want to measure. For instance, if I wanted to measure the terminal voltage of a battery, I would place the voltmeter across these two terminals. Now, an ideal voltmeter wouldn't affect the battery itself, but a real voltmeter does draw a little bit of current through this. Not enough, oftentimes, to really affect the outcome, but it could cause a current drop if the battery is actually generating a current. Likewise, if I want to find the voltage across resistors, I would place the voltmeter across the resistor. Again, you'd have some small leakage through the meter itself, but for most current voltmeters, it's really not enough to affect the overall performance. So again, voltmeters across whatever circuit element you're trying to analyze, ammeters through. So again, I have two resistors. Now I'm going to measure the current. Here, everything's in series, so whatever goes through this ammeter is also going to go through these individual resistors. In parallel circuits, you have to place the ammeter within each branch. Remember, ammeter, measuring current, we're measuring current through. So the current coming from the battery would be in series with the battery. The current going through this resistor right here, the ammeter would have to be in series with that. It has some small resistance in it, so it will affect some of the performance, but again, usually it's not all that much.